In order to relate one reference frame to another, we first need to define an event by assigning coordinates to it. These will differ depending on the observer's coordinate system. For example, in system S, we can have x, y, z, and t, while in S prime it will be x prime, y prime, z prime, and t prime. The system of equations that enables us to transform coordinates from one frame to another is called the Gaussian transformation. While these equations hold for classical physics, they fail when applied to the Maxwell equations, as unlike Newtonian physics, they are not invariant under the Gaussian transformations. This violates two of Einstein's postulates. In order to obtain equations that allow us to relate one reference frame to another in context of special relativity, the Gaussian transformations must be modified. This can be done as long as we keep the transformation linear and the symmetry properties of space are respected. Keeping this in mind, we can obtain the Lorentz transformation, which includes the boost factor.
Let's consider two friends, one an astronaut in a spaceship, which we'll refer to as inertial system S-, and the other at the space station, which we'll refer to as inertial system S. The astronaut has a clock at rest at the origin of the spaceship, which moves with velocity v along the positive x-axis relative to the friend in the space station. The moving clock records the lapse of a certain time, and we want to know the corresponding time lapse recorded by the friend in the space station. To answer this, it's helpful for us to have the inverse Lorentz transformations. There's several ways to find these, one of which is to find the inverse matrix to the Lorentz transformation matrix. If we look at the time difference in the inertial frame S-, we can see that it is TB- minus TA-, and the time difference in the inertial frame S will be given by TB minus TA. Looking at the equations, the inverse Lorentz transformation equations, we can see that CTA is equal to gamma C T-A, and the same applies for B. And so the time lapse in S is given by gamma times TB- minus TA-, which is the same thing as gamma times the time lapse as recorded in the inertial frame S-. We know that gamma is equal to 1 over the square root of 1 minus b squared over c squared. So gamma is always more than 1. Therefore, the time lapse according to the man at the space station will always be larger than the time lapse as recorded by that man in the spaceship.
For a long time it was thought that an object's length is a quantity that will remain unchanged until Einstein came and messed things up. Using the Lorentz transformation, we have to redefine what the length of an object actually is when it is not at rest. What we'll find is that different observers will actually measure different lengths relative to the reference frame. Let's pick two inertial systems, S and S prime. S being one where an observer is sitting on Earth, let's call him George, and he's watching stick-line Bob in that rocket in S prime. Second one, S prime, is the reference frame when Bob lays at rest in his rocket as it is speeding off at a speed near the speed of light. Measured in S, simultaneously we have 4 vector coordinates, and measured in S prime we have another 4 vector coordinates that are not simultaneous, where because S is simultaneous, S prime can't be, and S prime, what you can do instead is, because he feels like he is at rest, his length can be measured at any time without there being any problems whatsoever. Now, if we apply this Lorentz boost to the 4 vector coordinates in both systems, we can achieve two equations, 1 and 2, from the first elements of each one, where if we do equation 2 minus equation 1, we can reach this final form where this side is showing the original length, this is showing the new length, and you can rearrange to find that the new length is equal to a factor of 1 over gamma times the unchanged the original length, where the factor is actually root 1 over b squared over c squared, where if you plug the numbers into that, for any speed, any velocity, we'd find that the original length would actually contract as an object goes through space-time with a certain velocity.
Length contraction only occurs along the direction of motion. Let's consider the person moving at a speed v relative to frame S. In the person's reference frame, the S prime frame, she's at rest and has height h0 and is positioned at an angle theta to the x-axis as measured from the origin. What is her height in the S frame and also the angle theta f? In the S prime frame, x prime a and y prime a are both 0 since they are both at the origin, and x prime b and y prime b are the horizontal and vertical components of the person's height. If we measure both ends of the person simultaneously at time equals 0, and using the Lorentz transformation, we can get the points of the person's position in S frame. With the xb point, we use the x equation, and you can see that x is equal to x prime over gamma. We can see that yb is the same as y prime b. xb has been reduced from x prime b. Therefore, the person's height is only contracted in the x direction. And using Pythagoras' theorem, we can see that the height h in S frame is equal to this. Using the points in S frame, we can see that this is the value for theta s.